All right, how did you guys do with this one? All right, so for someone on the surface of a neutron star is a funny thing. It's after a supernova. Oftentimes, a star has experienced so much heat and so much pressure that the material of the star has been smushed so close together that the electrons have been ejected out and they're just neutrons that are left over. And they're very, 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 very dense. And so a neutron star, for perspective, this one is kind of a heavy one. It's a mass of 8 solar masses. And what's a solar mass? It's the mass of our sun, right? Which, if you take a look at that reference sheet from your textbook, is 1.99 times 10 to the 30 kilograms. Pretty massive, but that neutron star is 8 times the mass of our sun, but with a radius of 1,600 meters. And then just for perspective, our sun has a radius of almost 700 million meters. So it's pretty dense. Okay. So what we are going to do is calculate the gravitational field strength, which is lowercase g, and the weight of a typical human on the neutron star. So weight is the force due to gravity. A neutron star is very massive and a very compact package. As a matter of fact, if you took a teaspoon full of neutron star, just take a teaspoon and scoop a teaspoonful of neutron star, that teaspoon would have a mass that's the same as the mass of our moon, just for perspective. And so that makes it pretty crazy, because I don't know if you watch any like Avengers movies or anything, but Thor's hammer was forged in a neutron star. And so I imagine it's made out of neutron star, and it's much, 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 much larger than a teaspoon. And so that's why the Avengers is science fiction, because Thor's hammer would be, if you used to throw it, that would be dang near impossible, and it would be problematic for objects that it would be flying by. There would be significant gravitational attraction. Anyway, let's talk about these problems. Okay, so if you did this calculation, you would have gotten a gravitational field strength of 4.15 times 10 to the 12 newtons per kilogram. Right. And then for this problem, there's the easy way of finding the force due to gravity, and then there's the hard way. Let's do the easy way. Since we've already got the gravitational field strength, we can just take that gravitational field strength and multiply it by the mass of a typical human. Right, this is where that 70 kilograms will go. And so we can take 70 kilograms times our 4.15 times 10 to the 12th. Right, and then we get the weight of this person to be 2.9 times 10 to the 14 newtons, which I dare say is not survivable. Okay, so that's just your fun fact slash science fiction superhero trivia for the day. Okay, the last thing that we're going to talk about in this lesson is finding the orbital speed of an object that is orbiting a planet or something. So we can think of like a satellite orbiting around the Earth. So it's traveling in a circular path, which means gravity's force is the centripetal force. Oh no, we're talking about centripetal forces again. Yes, we are. Okay. So gravity's force is the centripetal force for an object like a satellite orbiting around the Earth. So gravity's force is Gm. So this would be the mass of the Earth, and our little mass would be the mass of the satellite over r squared, right? The distance from the center of the Earth to the center of the satellite. And the centripetal force is mv squared over r. These r's are the same. The distance from our object that's orbiting to the center of the circle, which would be the center of the Earth. This little m is the thing that's moving in a circular path, so that's the satellite, right? And so mass of the satellites cancel out. We've got one radius over here cancels with one of the radiuses over here, right? And we end up with v squared equals g times the mass of the Earth over r, right, which we can simplify to the speed of an orbiting object equals the square root of g times the mass of the Earth over the distance center to center. So that's the equation that you'll use to find the orbiting speed of an object. I don't believe that's an equation that's in any like IB resources or anything, but this would be the place to start. Okay, identifying that the centripetal force is a force due to gravity. All right, last example, and then we will set you loose on some problems. All right, so I'm including this example because it is written in a way that is common in problem solving using SI abbreviations, but I want you to remember distances in your equations should be entered in meters, masses are in kilograms, right? And that r in our equation is the distance from the center of one object to the center of another. Okay, so let's take a look at this example here. We've got a space shuttle that typically orbits 400 kilometers above the Earth's surface. Let's go ahead and convert that into meters. Above the Earth's surface, the Earth has a radius of 6,380 kilometers, right, which is 6.38 times 10 to the 6th meters. How much would a 2,000 kilogram part for a space station weigh when it has been lifted into orbit? Should we convert kilograms into grams? No, kilograms are the SI unit for mass. And it's asking for how much would it weigh. So it's asking us to solve for FG when it has been lifted to orbit. Okay, so we've got FG equals G m over r squared, right? 6.67 times 10 to the minus 11 times the mass of, big M will be the mass of the Earth, 5.98 times 10 to the 24th. Little m is the mass of the space station part, so 2,000 kilograms. And here's the tricky bit. R is the radius of the Earth, 6.38 times 10 to the 6, plus so that's the distance from the center of the Earth to the surface of the Earth. Then we need to add the distance from the surface of the Earth up to the space station. Okay, and then commonly people forget to add those together and then square them. Okay, so don't forget that squared. And you should have gotten 17,400 newtons. Okay, so put that in your calculator and make sure you can get the same answer as me. All right, and again, finding the gravitational field strength. Here, let's do this in a different color. Gravitational field strength is little g. You can do it the hard way. Little g equals big G, big M over r squared, or you can do it the easy way. Little g equals weight over mass. Let's do it the easy way. We'll bring this weight down. 17,400 newtons divided by little m is the mass of the space station part. 2,000 kilograms, and we get 8.68 newtons per kilogram, or meters per second squared. Okay, does that make any sense? Yes, because it's a little bit smaller than 9.81. That's what we'd expect on the surface of the Earth. And we know that as you get further away from the surface of the Earth, as you separate masses, the gravitational field strength gets smaller. All right, and then finally, determine the speed of the space shuttle at this altitude. That speed is equal to the square root of gm over r. Okay, again, we're putting in for r is both of these values added together, but this time it's not squared. And then this capital M is the mass of the Earth, and you should get 7670 meters per second. All right, make sure that you're able to get those answers as well on your own. Most of the problems here are not difficult for students conceptually, but simply getting them in your calculator correctly to get the right answer tends to be a problem. All right, so this is the end of this portion of the lesson. Take a look at section 4.7. That's what we talked about today. And then in the back of the chapter, if you've got a physical book on page 112, try a couple focus on concepts and then a couple problems. All right, please let me know if you guys have any questions.